Hello, everyone. We are very delighted to have Dr. Maxime Gariel. Dr. Maxime is a Chief Technology Officer of Xwing startup. He will give us a talk about Xwing, the journey to deploying autonomous cargo aircraft. Without any further ado, the floor is yours, Maxime.
Thank you very much, and thank you for the opportunity to talk this evening for you. So I'm going to describe and talk about Xwing, what we're doing. And so Xwing is a San Francisco-based startup that started about five years ago. And the mission of the company is really to change how people and goods move around the world for distances that are typically too short to fly commercial, but too long to drive. So think distances between, so in miles, like 100 miles to like 150 kilometers to 500 kilometers, where it takes like hours to drive. And in some cases, even longer because you don't have good roads and infrastructure in between. A bit of background about myself and why am I talking to you? So in this talk, you're not going to see a lot of graphs like the previous speakers. It's going to be more about how do we transition from research to the industry and to have products. So I got my undergrad back in France doing aerospace engineering. Then I worked for Thales to do category 3 autopilots for the Superjet 100. And that's when I really discovered my passion, which is to make airplane fly themselves. I think this is something that we all have in common with the previous speakers. But it was amazing to go from the conceptual controllers to putting that on the aircraft and seeing some other results. Then I did my PhD with Professor Feron back at Georgia Tech, where I was looking at air traffic management and what happens when you put more and more automation into that very complex system. And when the system starts failing, what are the backup mechanisms that you always need to have in place in case your fancy or your complex system starts failing? Then I went to MIT to look at how to improve general aviation using ADS-B for conflict detection and avoidance. And then I spent a number of years at Rockwell Collins Control Technologies, working on the helicopter project that is on the right, where we took a manned helicopter and made it fully unmanned by adding a triplex redundant flight control systems. So that is adding 3 sets of computers, 3 sets of sensors, and a bunch of actuators to be able to remote pre-flight, engine start, takeoff, navigation, landing, and landing even on a moving platform. I was in charge of safety redundancy at first and then became the chief engineer. Give me a really good picture of what it takes to go from a manned aircraft, which is, with all the traditional steam gauges, to an aircraft that is kind of fly-by-wire with the right level of safety to be able to put people on board. And I joined Xwing back in 2016 when we opened the office. And on the side, I'm also a pilot. So between the pilot experience, the flight controls, and the air traffic management, gives me a really good overview of what it takes to change aviation into rig autonomy, because the flying piece is only a tiny subset of solving this problem. The flying piece, as I'll say later, is like the easy part. To do it well, it's not that simple. So don't get me wrong, right? It's not super easy, but there's a lot of other problems that we need to consider to make airplane fly through the airspace safely. So what is Xwing doing? So Xwing is building a software-defined middle-mile air transportation network. So it's not just the aircraft, it's really bringing autonomous flight technology as well as the operations. So that is the controls on the ground, the interaction with air traffic control, the dispatch capabilities, so that we can change how regional transportation is done. We can revitalize local communities using what we call teleoperated regional cargo aircraft. So autonomy is the final goal. And as a very pragmatic company, we start with teleoperated. It doesn't mean that we're going to have a pilot flying, with a stick and rudder, stick and pedals on the ground, where it's going to be monitoring the aircraft on the ground to be able to see and to discuss, to talk to air traffic control. The first market we're targeting is what we call the $1 billion middle-mile express air cargo market. So to give you an idea, when you ship a package overnight, what happens is, we're going to talk about the second part, where you have the FedEx, UPS, DHL airliner that flies in a major airport around 5 a.m. And then it unloads a bunch of pods from that aircraft, and those pods are either loaded back onto small vans or they're loaded onto smaller airplanes like what we call feeder airplanes, Cessna Caravans, for instance, to do another trip like 100 to 200 miles to the local airport. And that aircraft has to depart around 7 a.m. to land before 9 a.m. at that destination so that it can be loaded into a van that will deliver it to your door or to your company's door by 9 a.m. So it's really the express and the time critical market that we were targeting here initially. Eventually, this technology can be applied to a lot of other markets, but we believe this is where things can start, where public acceptance is going to be easier, where the risk level is minimal. What does it look like in the US? So in the US, we have over 5,000 small airports. It's pretty unbelievable when you think about it. 90% of the population lives within 15 kilometers of one of those airports. And this, what you see here, is the air cargo network with the shorter routes in the US that's flown on a daily basis. So it's a really interesting market to get started. The teleoperations that we're building can think about take the pilot, put into a control center, and what we call the network operations center, where you have a number of operators that can connect to an aircraft when the aircraft is ready, can set it up, then can load the flight plan according to the route, or can tell the aircraft to generate the flight plan. Then they're going to talk to air traffic control, because that's one of the items that's going to take a long time to automate. So they can talk via voice to air traffic control, get the right clearances, modify the flight plan if needed, or tell the aircraft how to modify this flight plan. And then get going, right? So tell the aircraft it's okay to get started, get to taxi when we approach the runway, get the right clearance to take off, and so on and so forth. So the operator can supervise the flight. But at the same time, right, this operator cannot be relied on for the entire flight. The aircraft have to operate autonomously. They need to be able to do everything on their own, since the link between the aircraft and the ground cannot be effectively trusted. Communication at such distances is really challenging, really hard to get reliably. So the aircraft can do everything on its own. So they can optimize. It can optimize the trajectory, has dynamic path planning, can taxi, take off, do the navigation, the landing, as well as handle all of the emergency situation. Go through the checklist and decide to reroute as needed to broadcast emergency, transponder codes, and so on and so forth. The aircraft is fully equipped with a full engine control, airborne detect and avoid communication with ATC, as well as with our network operations center, and redundant actuation and processing. How do we go from a remotely operated aircraft to full autonomy? We've sliced and diced the problem many different ways. And since it's going to take time, our approach is to bring initially only what is necessary to be able to fly in the airspace. So what that means is you take a perfectly good aircraft, like a Cessna Caravan in this case, you see on the picture. You add three main components. The first one is detect and avoid. So the ability to see other aircraft around and safely avoid them in the air as well as on the ground, right? Taxiing is a very important part of this problem. Then you have command and control. So this is the ability to have communication with your aircraft at all point in time, or most of the time, I should say. And finally, digital flight control. So we need to ensure that we have redundant actuation on the aircraft fail-active system so that if any component fails, the aircraft is able to detect it, reconfigure, and keep on flying safely. With those three main components, we are able to start remotely operated cargo aircraft under Part 135 or initially Part 135 with some exemptions. And then at the bottom, you can see what we're doing is we can develop path planning, enhanced autoland, taxiing, GPS denied positioning, automated ATC, contingency management in a way that the aircraft can do most of it, but not necessarily have to be certified to get started. If we keep the human in the loop or over the loop to validate some of those decisions, that allows us to start without certifying every item. That is going to, as we push that, is going to reduce the operator workload to a point where eventually we can have one operator overseeing multiple aircraft. What does that do in terms of, why does it make sense? If you think about the aircraft right now, for the cargo market, every morning, the pilot has to wake up at 4 a.m. to be at the airport at 5 a.m., do the pre-flight check, wait for the cargo to be loaded, fly for about an hour, and then sit all day in a hotel room until 5 p.m., where they do the return trip to bring the packages back. So it's not a very exciting, job. Pilots only do it so that they can get enough hours to move on to the larger aircraft. So there's a lack of pilots right there. But at the same time, if you have to fly 7 days a week, it means that for each aircraft, you need to have at least 2 pilots. So we're talking about 2 pilots per one aircraft. In this case, if you have one remote operator that can fly one aircraft, for an hour, that can switch aircraft. So effectively, you can have one operator for 3 aircraft, right, on a given day. Since it's 7 days a week, it's not exactly as much, but the ratio of operator per pilot from the get-go can be much improved. So the team that we have, we are bringing together experts in all fields that are related to this problem. So it's not only unmanned aircraft and controls, it's really people that have experience doing unmanned aircraft controls, but also like FAA regulations, people that have worked on certifying various types of aircraft, rewriting in the US, the Part 23, so the certification of small aircraft, air operations. So on the Part 135, so on the operator side, the airline side of things, working on modifying or applying to modify some of the regulations, some of the manuals that we need to have. So it's very heavy on the documentation side. Experts on the robotics side, so people coming from Uber, for instance, coming from self-driving cars, as well as software. I have a short video that we unveiled last summer. Hopefully that will play nicely.
Autonomous aviation is coming. It's going to revolutionize the way people and goods move around on a regional level. It's going to introduce a new mode of transportation that's going to change the way society functions in general. And at Xwing, we look to lead the charge in that area by developing some of this key technology to make it happen. We bring together people with deep expertise in unmanned flight, and we pair them with some of the best software engineers that the Valley offers. It's this mix of talent from different industries that I think has the highest likelihood of creating successful outcomes in this space.
Xwing's autoflight system is really the brain and muscle of the aircraft. It completely replaces what a pilot does. The autoflight system is able to wake up the aircraft, to turn on the system, to taxi the airplane on its own. Through radio relay, we can talk to air traffic control to get the right clearances. The autoflight system makes the aircraft take off on the runway, fly through the airspace, brings the aircraft, lands, taxis back all the way to the gate, shuts down the engine. all that without the intervention of a human.
The market that we target is the cargo feeder market. It's going to be one of the first applications for unmanned flights in the industry in general. Confining our initial unmanned operations to cargo over unpopulated areas allows us to sandbox, these initial commercial operations in a way that puts the regulator at ease.
The features that make the Xwing auto-flight system stand out from the competition is that it does full airspace integration. All the coordination with air traffic control with other aircraft, dynamic planning in the air and on the ground. Additionally, the system is designed to be platform agnostic, to be able to be installed in any type of aircraft. It allows full autonomy of the entire operation.
We're trying to do something here that really hasn't been done before. There's not a playbook for how do you certify autonomy in aviation. It just hasn't really been that mature to this point. So we are working very closely with the regulator and with other industry bodies to figure out what the right path is.
I think there's nothing more exhilarating than having your baby or effectively your aircraft do its initial maiden flights.
Sitting in the airplane when everything is coming to an end, I should say, it's an amazing feeling of pride for the entire team.
So we look to fill the last remaining gap in the transportation network. It's going to connect local communities better than ever before. And that's enabled by the technology we developed here at Xwing.
All right, so that was last summer then when we came out of Stealth, really announcing what we were doing. One of the reasons that we picked the Caravan, as I mentioned, is first for the cargo, but also you've seen a lot of movement on the eVTOL space. And one of the key pieces to make this happen is to have autonomy. What we believe is before eVTOL can really be deployed at scale, you need to get some of those components right and ready. And by not doing everything, by not developing a new airframe, not developing a new propulsion system, as well as the autonomy and the infrastructure are required for eVTOLs, just focusing on the autonomy piece is going to allow us to deploy much faster. And then once we have that piece, we can add electrification and a new airframe and so on and so forth. So it's really about getting to market without needing all the those building blocks. So it was very exciting about last summer. We actually brought on quite a few reporters to come for a ride. There were some of the few people in the world that have been able to fly an aircraft from takeoff to landing without a pilot touching anything. There's a number of drones, but drones where you have people on board, not too many. So that was amazing. So where are we right now? So we have 5-axis custom autopilots where we have like 3-axis raw pitch yaw, the throttle, as well as differential brakes. We can do gate-to-gate missions. So from being stopped on the ramp in front of our hangar, taxi all the way, go around the takeoff, navigate, avoid other aircraft, and come back for landing and taxi back. All that we talk to heavy control. They give us, what taxiway to take. We just input like Alpha Bravo Charlie, and the aircraft takes care of everything else. We have way over 100 autolands and AutoCAP. That's when I wrote it. I myself have about 100 being in the aircraft. We've operated at multiple airports, including high altitude. So it's really nice. We are close to the mountains. So we go sometimes fly in the mountains to evaluate performance of the autopilot with high temperature, high altitude, so low density, and even to never seen airports. One thing that we've done where like the entire team was super excited was over the summer. The Navajo Nation in the US, so Native Indians, has been very affected by the COVID pandemic. They're a nation that lives on really large land and very almost no infrastructure. Like they sometimes don't even have water, running water, and they live in communities, in houses where you have generations at a time. So they were some of the most impacted people in the US. So what we did is we gathered a bunch of personal protective equipment from organization in the Bay Area, and then we went to deliver on an 840-mile trip. So PPE as well as tablets for kids, other equipment for the people of the Navajo Nation. So for us, it was a way to demonstrate what are the capabilities of the system and how can it change how people live. So we did this trip 840 miles without intervention of the pilot, from takeoff to landing, and landing at an airport where we had never been before. We learned a lot, including how much you can trust of what you see in terms of databases. So it's always good to push the boundaries. We are able to do remote operations. So we have a certificate from the FAA to fly either from onboard the aircraft in the back, as I will show you, or fly from our control center. And we have automated ground and airborne path planning. So what I was showing here, this video. So before I play the video, what you see is we have on the aircraft radars, ADS-B, cameras, and LiDAR. And in this case, we are fusing the four cameras, and two of them are overlapping in the front. So we are fusing all those cameras. In this case, that was on the way back from Arizona, where we do our delivery. We went to the airport called Sedona. And as you can see, it's extremely challenging airport. You will see it on the left a bit later. But you approach where you're flying in the canyon. You have really high mountains on the side, and you fly super close. So that was great to look at the sensors, how the radar works when you fly like below the mountains. When on your approach, even for landing, you cannot rely on your radar altimeter. So the airport is going to appear on the left. So we're going to fly just above this hill. Then you have a valley here, and then the airport on the left. So all that you're saying right now is automated. In that case, the runway also is sloped, has a significant slope. And this is something that we had not accounted for. So in that case, you'll see the pilot will disconnect because we're landing at a 3-degree glide slope, and the runway is sloped about also at 3 degrees, which means that we would have never touched down. So great learnings to try, and that's the advantage of having a safety pilot when you do these operations. You can try new things and not be afraid of pushing the boundaries. So that's an example of how challenging it is. You see, you have like this cliff all the way to the threshold of the runway. So you really have to be confident in your other measurements to make sure that you don't hit. If you're too low, you're never going to see it until you hit the cliff. So at that point, the system is still on. And as you can see, we're slightly to the left of the runway, which also shows how much you can trust databases, right? We had used the runway information from the FAA, but it's still a few meters to the left. So as I mentioned, airborne detect and avoid is a key piece of technology to enable the integration of unmanned aircraft in the airspace. We've been working on this problem for a number of years now, and we started also with a partnership with Bell. So Bell is developing a family of aircraft. You can see here at the bottom left, vertical takeoff and landing vehicles with a range of payloads from 20 pounds to over 1,000 pounds. So they scale up this vehicle. And we partner with NASA and the FAA on this project called US in the NASA, so Unmanned Aircraft System in the National Airspace System, where we had integrated our detect and avoid system onto that vehicle, as well onto one of their helicopter. Performed about like 40 hours of flight on the helicopter and about 10 on this APT-70. Ran encounters, planned, unplanned encounters, collecting the data, tuning the radars, because radar works really well when you're at high altitude, but when you get close to the ground, you start picking up traffic on the ground, terrain, reflection on buildings. So very challenging to use this type of system. We've got like hundreds of flight hours at this point, and encounters planned and unplanned. And on the certification side, our approach is to mount our detect and avoid system using what is called an STC, so certified to be mounted during operations, but collect the data to demonstrate how well it works. And once we have that, we'll do the next step, which is to certify that it can be used to control the aircraft. We've taken a very active role in various standard committees, so ASTM F38, F44, as well as RTCA SC228, to help define some of the requirements and how and why the system should behave the way it does. That's going to show, this video is going to show an example of our system in action. That was back last summer. Lots of progress have been made since then. Once again, what you see is the fused view of the 3 cameras. This is a top-down view of our aircraft in the middle, other traffic around. And then that was taken last summer during we had like major fires in California. So we're like flying above the smoke. So that's why it looks a bit surreal. And the other aircraft, N84 Victor Charlie here, is flown by one of our test pilots. In this case, it's a head-on encounter where we offset by 500 feet. But we tell the system, we kind of tell the system that we need to avoid by more than 500 feet vertically so that we can have a safe encounter, and at the same time, the system is going to react accordingly. And on this top-down view, it's like the red indicates that if this is the location in space of where the conflict is going to occur. So if this red is on your blue line, which is your trajectory, then you're going to end up really close from the other aircraft. And the yellow and the orange are like represent like various distances and severity effectively. So in this case, right now we are only using ADS-B. And as we get closer, you'll see the other aircraft gets into radar range and then in a camera range also. So we fuse those 3 sensors to provide the best estimate of the position of the other aircraft. So ADS-B comes in at 1 second interval, and the radar and cameras are much faster. Here, like it comes to radar, camera, we're tracking it, then the information is sent to the autopilot, and we start the overlance maneuver. So in this case, it was the minimum distance was actually not quite enough. We had not accounted for some latency actually. So those things have been corrected since then, but that shows also the importance of running some of those tests. Not only doing software in the loop simulation, but also hardware in the loop and flight tests, because you need to test integration at all levels. Yeah, I was saying it's a problem that seems relatively easy, but when you start thinking about all the cases, that's when it gets difficult. What happens when you have 2 aircraft at the same time? What happens when you have an aircraft and you have terrain also that you have to avoid. What happens when somebody comes from the left and you start making a right maneuver and you end up, having a parallel track? How do you resolve the next step? When do you stop, making like stupid turns? So lots of cases to take into account. And that's when, going from the academic paper where it works to make it work all the time in all conditions become very, very challenging. And we just talked about what happens when we are airborne. The next step is, let's do that on the ground, right? Taxiing is extremely, it's not the same speed. So the sensor modality is different. We don't need radars. In this case, we're mostly using LiDAR and cameras. But it's a very important piece of the autonomy. The airport environment can be, as I'll show in a few slides, very challenging. So in this case, you can see like we have equipped the aircraft with a couple of LiDARs, and you can see, radar return, LiDAR return. And then in this case, it's the next level where you start building objects and tracking if they're like objects that are moving or not moving, so that we can join the safe path for the aircraft. So it's moving from being on paper to doing things in real time, process all this data, deal with all the environmental conditions at all times. So it's very exciting to to implement a lot of the work that we can read in papers. So in this case, we are relying on automotive developed sensors for those operations. We believe our problem is simpler than the self-driving problem, right? You don't have grandma chasing a duck in the middle of the road, or hopefully we will not have that at the airport. Not having like, a guy carrying a stop sign or all the crazy things you see for self-driving cars. But at the same time, we are able to leverage a lot of the sensors technology and also the skill set that people are developing here. Living in San Francisco, I see self-driving cars from Waymo, from Cruise, 10 times a day. The city is, those cars are roaming through the streets, and what is great is that then you can hire the people that work on that and bring this technology to airplanes. All right, so how does our test work? So on the left, it's our control station on the aircraft, which allow us to do things much faster so that we don't have to go through a data link. So on the right-hand side, this is the flight control station, where I've been sitting for most of the time. And then on the left-hand side is more the autonomy, so high-level type of decision-making, detect and avoid. So fusing all the sensors and deciding on what is next for the flight controls. In the video that we talked, Ed says that the system is agnostic. So to be of the types of vehicle, we have to be to put a caveat here. Flight controls are going to be very tied to the aircraft itself. The autonomy portion will need to know or needs to know about some vehicle dynamics, as was discussed in the previous presentations. But the decision making, if we know about the dynamics, can be agnostic of the vehicle type. And on the right-hand side, this is our control center where we downlink video in real time. And the operator is able to talk to a traffic control and monitor all the same information that we have on the aircraft. Finally, I believe that the best way to develop the right product for the market is to start operating. So we have acquired what is called a Part 135 operator certificate. So we are an airline. We can carry cargo and passengers, but we only focus on cargo for revenue. So we've been operating, or actually we operated for UPS during the peak season, so the holidays, with 3 Cessna Caravans. And the objective is really to understand all the requirements and all the non-aerospace need. The flying portion are well understood, but what else goes around when you have to run this operation. So building the aircraft in a vacuum is not gonna work. So what you see here is people loading the aircraft. So it's funny because we're talking about unmanned aircraft, but when they're loading the aircraft, they have 10 people passing packages, weighing them, putting on the aircraft and building the Tetris at the bottom right. So those are other places where we're trying to figure out, like, is there a better way, more efficient way to solve this problem and to make it fast and save time? And then this video shows on the ramp, so in Phoenix, the UPS ramp where all the small aircraft are being loaded, and suddenly it's 7:30 a.m. All the aircraft start the engine at the same time and start taxiing. So you will see why the taxiing problem can be very, very challenging. So you have this aircraft that is taxiing, you have people all around. This is one of our 3 caravan. You have people, walking, tons of people, tons of aircraft. Then you have to go around. Everybody parked. There is no line marking to be followed. So really, it's a dynamic path planning problem that has to be solved with obstacles that are moving. You can see like the large airliner. So another aircraft starting its propeller. That's the large airliner that landed a few hours back, and that also leads to all the small airplanes. Flying is the easy part. The difficulty is to do it safely, repeatedly in all conditions. And I should say that the taxiing is also not that simple. So thank you for the opportunity and your attention. Stay tuned in the coming days and weeks. We're gonna be having more announcement about what we're up to. I wish I could have shown today, but it's a bit ahead of the schedule. And I think we have a few minutes for questions.
Okay, so this question from Eric. He asks, in Saudi, we have a lot of desert area. What are your minimum requirements for landing? Can you handle a dirt landing?
At this stage, we haven't. We've been landing on runways. I don't think the dirt landing would be a major problem, but it's not something we have tried yet.
Okay. We have other questions from Bilal. He asks, he says, thanks for the great talk about the promising company. Can you touch a bit on precautions in case of cyber attacks or communication issues with the aircraft?
That's a very good question. So yes, this is definitely an area that we have to be concerned with, and we need to focus on. So we are applying encryption at various levels throughout the communication layer, and making sure that we have a way to authenticate the communication, so that cybersecurity is, it's always a very important requirement, and needs to be accounted for.
Okay, thank you. We have another question. What communication technologies do you use to communicate aircraft and the ground station? What range?
Yes, so we are looking at the range of existing communication methods. So ranging from around the airport, you can use on the 900 megahertz spectrum, 2.4 gigahertz for video. So this is not command and control link. This is just for video and telemetry. Then we're looking at the CNPC range, so command and non-payload communication spectrum in the 5.3 or 4 gigahertz. So it's a spectrum that is allocated for control of UAVs. That again is line of sight communication. So we're talking about 50 to 75 miles if you have the right pointing antenna. And then beyond that, looking at SATCOM, so between the existing and what is coming up, the new entrants, like for instance, Starlink, possibly could be a way to have like low latency, high bandwidth communication with the aircraft. And then there's also some companies that are building ground-based networks for command and control. So we're in discussion with those companies to see where they have some infrastructure to start testing that. So really, we're exploring every single C2 link that exists. It's not something we want to develop, and find the best combination, as well as the price is a consideration. Satellite is great, but right now it's very expensive.
Okay, thank you. Here a question also from Pan. Do you have a plan to move to VTOL from fixed wing as your future aircraft?
In the long term, but for us, first step is to build all the autonomy necessary, focus on using existing infrastructure and solving this problem. What we believe the next step will be is electrification, and after that the VTOL. But the VTOL, there's a lot of challenges to address. They need to address the electrification problem first, and then infrastructure, and then your range is very limited, given the energy required for takeoff and landing. For cargo, we need a bit more payload, but in the it's in the long term vision.
Okay, thank you. I think we can take one more question. Here's a question from Eric. Okay, what role does ADSB in out play with your system?
So ADSB in and out are used as one of the modalities for detect and avoid. It's not mandated everywhere, so we cannot solely rely on it. When it works great. It provides great information at long range. But we need to be able to detect what we call non-cooperative traffic, so people not equipped with ADSB and not equipped with a transponder. So that's why we are using radars, and in the future adding cameras. But for those non-cooperative traffic, radar is the source of detection.
Thank you, Dr. Maxime. I think we're going to. It was a very interesting talk.